I'm going to introduce what hydrochemistry is and how it differs from conventional geochemistry. I think that's a really important part, if explorers are interested to use this technology, and how to use hydrogeochemical data, and also the relevance of regional data. It's not just the data that you collect, but the regional data in terms of data interpretations. I'll touch on the concept of national hydrogeochemical database and how it sort of translates from national to state scale data for data interpretation. And then that sets the scene to get into the Eastern ISA project itself, and followed by a brief summary. The hydrogeochemistry differs tremendously from the conventional chemistry. When we talk about conventional chemistry, we are talking about rock chips, stream sediments, salts, and whole rock itself. And it's generally, the first difference is that it's confined to the top few meters of the from the ground surface. For hydrogeochemistry, there is no limit of dimension because it's a combination of water from above the collection point, below the collection point, and laterally. And we don't really know how far it extends vertically or laterally. And therefore, it is a chemically combined sample representing that sample itself, because we can't be certain how far the sort of influences is. There is a sort of calculation that I'll talk about it later on. The other thing about hydrochemistry, the difference is that firstly, it has no dimension. Secondly, the chemistry varies. It's not like a sort of conventional chemistry. When you take a chemistry, you can analyze it for 10 times and you expect the results to be the same. For hydrochemistry, it's different because it's dependent on the pH, the EH, the presence of flocculants, the presence of anions, oxyanions, the temperature, and that's a lot of things that are affected. And also, it's very much dependent on the amount of mixing, whether it's from surface, below, or laterally. And if you keep the sample for too long, it changes as well. And therefore, it is a sample that has to be used quite carefully, and you need that dimension, sort of, or comparison against a backdrop before it's useful. For most of the water that we collect, it's from extraction holes. Basically, when you extract water from groundwater, it sort of draws down the groundwater to form what we call a drawdown cone. As a result of that drawdown cone, you get a differential pressure within the drawdown cone that drives water from deeper, sort of levels upwards. And therefore, the water you collect only represents the mixing chemistry between the drawdown cone and the upwelling sort of water. And so it is pretty hard to use data sets, and it has no dimension. It sort of, varies from season to season, from time to time, from, day to day, if you want to see it that way. Australia is a huge continent, a very dry continent, and therefore the benefit of that is there are lots and lots of borehole database. The borehole are generally, drilled by so many players in this field that, the quality as well as the amount of data is so varied. The state government in every state in Australia has a really good collection. That's because most borehole needs to be registered through the government. It's a government sort of registry or data sets itself. However, the disadvantage of this government data set is that it has a lot of physical entities to describe the holes, the location, depths, etc. It has very little chemistry. The other smaller data sets is the data sets compiled by environmental study, by mine monitoring, by ecological study. This is a real small data set, but it has lots of chemistry. And so we are trying to sort of balance between the two. CSIRO has done an excellent job by compiling all this data into one data set. And it's not just a matter of compilation, it's a matter of QA, QC, and validation to enter this. And only data that fits the criteria gets entered. Basically, they look at the cation, anion, sort of balance, the quality, the range of elements, and if it fits that criteria, it's been entered. To maintain the high quality of data, CSIRO encourages everyone to use a field guidebook that they produced and a few data entry books. Basically, the data entry or the field data book prompts you to collect the sort of metadata required for the hydrogeochemistry. Recently, they've developed an app that you could load on your tablets, and it has all those tick boxes where you tick this instead of entering in a hard copy paper itself. Also, it's linked. If you had a field server, you could directly dump your data day to day or week by week, to their depository so that you don't lose data. And if you want more information about that, contact Nathan. He is one of the coordinators of that database itself. For Queensland itself, we had lots of data, and there are two sites that are put here, two links that are put here that you can access the data. One of them is the CSIRO, hydrogeochemistry database, which is released, through CSIRO or through the Bureau of Meteorological Explorer website itself. The other one is the Queensland Borehole Registry database, which is available through the Departments of Natural Resources and Mines. And that's a link that you could get all the data, very little chemistry, but it tells you about, how deep it is, where the springs are, etc. Next, we move on to the relevance of regional database in data interpretation. This is a good example where we plot the sulfate chloride ratio of the groundwater in Australia itself. You'd realize that, the water in the Yilgarn, the Hamersley, the Northern Australia, and down, to the Growler Plateau itself has high sulfate chloride ratio. That's because it's oxidizing sulfur minerals and then liberated it as, sulfate in solution. This is not a straight, sulfate chloride ratio. These are looking at deviations from the evaporation train, from the sulfate chloride, train expected. And so the results you see here, the red colors are ones that deviate more from that, evaporation train. The other thing you realize is that in Eastern Australia and undercover, it has a low sulfate chloride ratio. If you just look at individual results, we had two examples here. One is the Jaguar Bentley deposits in Western Australia, Northern Yilgarn, and the other example that we show is the Little Eva and Dougal River this is from the latest results we collected, in the East Australia results. If you look at the first example, you see that it has really low sulfate to chloride ratio. And if you do not look at the regional pattern, you think that, oh, there's nothing there and sort of move on. But if you look at it in the context of the regional pattern, you know that it's an anomaly. What happens here? In a closed system, the sulfate, it's like a closed system. They compete for oxygen, and the sulfate's oxygen is probably being taken up by other elements, and so it gets reduced to probably disulfides or sulfides itself. And so it doesn't, it's not stable in water anymore. It drops out of water. In that case, it forms a low in that region, and so it is an anomaly. Whereas in the Teutonic Bowl, which is just north of that Jaguar deposit, it has a high sulfate chloride ratio. It's because it's directly oxidizing sulfur in an oxidizing environment. And so the sulfate is held in stability in the water itself. In the East ISA study, we find that there's a lot of, the background, it's pretty low in sulfate to chloride. However, if you look at the two deposits, Little Eva and Dougal River, you see very high sulfate to chloride ratio. That's because it's in an oxidizing environment and the sulfate is still stable. Well, that's one of the examples why we need the regional pattern, for the interpretation. It's not just that sample, that bowl water, and you can use it for interpretation. The second example we are going to look at is the fluoride. The East ISA region has really high fluoride content in the water itself. And fluoride has implication for exploration and health as well. If you just look at the East ISA results, you probably dismiss it, oh, it's, there's nothing, anomalous about it. But if you look at it in the context of the regional data, you find that that's an anomaly. And it's not just analytical problem, because we have compared the results against previous work and it picks up consistently as high fluoride area. What's the implication? We just take note of that high fluoride area. That high fluoride area also matches with high tungsten. What's unique about this is fluoride tungsten association is really strong in that part of the world. Well, have we got a tungsten anomaly? We can't tell. It's because in isolation, that database, that package of data has no comparison. So we know that it's high, but whether it's related to lithology, to mineralization, or it's just high tungsten in the whole area, we can't tell. And that demonstrates the importance of regional data in this interpretation. Also, that example illustrates the importance of knowing what's anion that you have, anion or oxyanion. What's meant by oxyanions are anions that has different oxygen attached to it, like SO2, SO3, SO4. These oxyanions generally hold cations in a stable state in solution. And we have examples from New South Wales and Western Australia, where oxyanions hold things like vanadium, moly, tungsten, arsenic, and antimony stable in solution, or germanium, tin, and bismuth, etc. So it's been shown that oxyanions are important to hold things in solution. In this case, in the East ISA sort of database, we weren't sure because of the isolated data whether it's just because of the fluoride it holds the tungsten in solution, or it's actually anomalous itself. With that, we launch into this East ISA project, and I'll show you. For the East ISA project, we've collected 302 boreholes over an area of about 10,000 square kilometers, all the way from McKinley up to Kamilaroi. Before we do the sampling, a very important step is to do the sort of pre-planning to find out where do you position the hole, how far apart do you position the hole, etc. In this case, we look at the structural fabric of the Mount Isa area, and we find that most fault fractures, joints, etc., are less than 5 meters apart. And it has a northwest trending, sort of trend in most cases. Using those data, we could sort of guesstimate that, the area of influence of that hole is about 2.5 kilometers radius, or a 5 kilometers sort of diameter around the hole. Using that information, it's really critical for the planning, because we could plot all these things as triangles, on that study area with slight elongation along north-south due to the preferential north-south trend, and pre-plan the boreholes that we want to select. This gives a really good coverage of the whole area, and then it gives a good chemical signature of what's underlying. In terms of sampling, it's very easy. Firstly, you locate the sites. In this case, we pre-plan the sites. You go to the sites, you sample it either through Bella or through existing pump. You do field testing, where we tested EH, pH, temperature, and conductivity. And then you take 4 samples. The first sample is a 1.2 liter samples with salt, sodium chloride, and a sachet of carbon added for gold and analysis. The second sample is an unfiltered 100 ml for alkalinity test. And the fourth samples are filtered samples, 100 ml filtered sample using a 2 microns filter for cations and anions. And all samples are dispatched to CSIRO in Adelaide for testing. Simple. Well, not quite, because when you get to the field, instead of a simple sort of book that you can go and sample, the boreholes, so 302 boreholes probably has 302 different sort of versions of it. It varies from, windmills to solar, to electric pumps, to high pressure, to open wells, conceal, open, etc. And so when we go there to take, information like water table, site contamination, etc. We had to be very careful to see, what sort of, conditions it is in, and then we had to record all this. And then we collect sample. This is an example where Dominic has dismantled the whole piping system to collect the sample, and we got to reassemble the whole piping system for collection. And then we do the field testing and sampling and tagging, etc. Well, what's the benefit of hydrogeochemistry over the other sort of conventional chemistry? The first one is that it enables you to go into greenfield exploration and develop targets undercover. Conventional exploration is limited by how far the chemistry or chemical signatures could penetrate into the ground or from the ground upwards. In hydrochemistry, it's governed by, water, and so there is no dimension literally. And so it enables you to go as deep as possible because the boreholes are props right down to the bottom. And so, you could collect water from deep within. And so it enables you to do exploration in basins, undercover, as well as for blind deposits in outcropping areas where you do not see mineralization signature at surface. You do not see the chemical signature at surface. But if you could get water from underlying sort of formation of rocks, it's composite from every sort of direction, up, down, laterally. And so it still gives you some chemical signature. So that's the main benefit of hydrochemistry, that it expands the depth and laterally, the area of exploration. The second benefit is you do not have to be data intensive. As we mentioned, in the northeast Queensland, a borehole has probably 5 kilometers area of influence. And so you can afford to take very sparse low density sampling in that part of the world to represent the area or the area of influence there. And this contrasts against other methods where you've got to take meters apart or tens of meters apart for conventional surface chemistry. That's the first benefit. The second one is the results. You can look at it. For hydrochemistry, we analyze for 72 results, chemical results, cations and anions itself. So it gives you the breadth of chemical elements as well as anions, where you could play around with it to find out, what's underlying it. And so that you can look at the anomaly, from single elements or from multiple elements. From single elements, for example, if you got a high gold, you got a high gold vein. If you got a high silver, it's high silver. You could directly relate the water chemistry to what's underlying it. It's a powerful tool on its own. However, a preferred tool is to look at multi-parameter, sort of appraisal to find alteration signature. We use the word parameters rather than geochemistry because we include both physical and chemical parameters in this case. I'll give a few examples, which I'll sort of show some of this, diagrammatically later on. For example, for a sulfur alteration of a system that comprises arsenic, moly, and tungsten, you expect two things. One, the breakdown of sulfur to sulfate. You expect a high sulfate in that region if it's an oxidizing water. With the oxidation of these sulfides into sulfate, you also liberate the cation. So it will liberate also the arsenic, moly, and tungsten, together with the sulfate. And if you have the combination of these suites of elements, you could be quite confident that there is a breakdown of sulfur or sulfide alteration underlying it with that sort of, mineral assemblages. This has been done, over many parts of the world and in Australia as well. And so there are some, what we call a mineral indices created for the different type of mineralization. For example, for the VMS, the volcanic massive sulfide deposits, which is sulfur-based ones, you expect sulfur to be associated with copper, zinc, platinum, and silver. And that's a common association. And if you've got a better characterization of the deposits, you could even expand the list to find, whether it fits into the model or not. And another example, which is more prevalent in Western Australia, is the nickel sulfide, the Kambalda type of deposits, where nickel is associated with cobalt, platinum, and sulfur. And if you got this combination of elements, it's an indication you got a nickel sulfide system there. Well, we've been talking about sulfur a lot, but it need not. It's not compulsory to have sulfur in the system to be able to use hydrogeochemistry. A good example is this. The Archean sort of gold lode in Western Australia. It's lots of work done in the northern Yilgarn region. And without sulfur, you could still use elemental association. In this case, for the Archean lode, gold, arsenic, moly, and rubidium are really diagnostic of this sort of ore system itself. Well, besides chemical elements, you could also use, just thermodynamics or chemical dynamics. In this case, you can look at saturation indices. For example, for uranium, you can look at saturation indices for uranium. The other thing is that, the element chemistry could be put together to determine lithology and aquifer. And also for environmental study, which is probably the sort of, baseline for that. This is an example of the combined data sets where the stars represent the data we collected in the last campaign, and those triangles and dots are ones from our previous work. And it shows much more clearly in the pH plots where you see the new data against an old data. For results, we talk about lithologic mapping. You know, this is an example where we had high silica, high strontium calcium ratio, and this coincides really well. And you could basically say those high silica, high strontium calciums reflects shallow sort of cover over the Mount Isa region, and it's mostly samitic or felsic rocks there. There's a sort of enigmatic sort of question is this vanadium. We saw vanadium distributed within that region, and after sort of processing all the data, we think it's related to unexposed Tullabug formation, which has high vanadium in that area. So it's able to sort of map not only lithology, but also the basement sort of unit as well. And another example is that this fluorine tungsten ones that we mentioned, it's really high in the great artesian basins. And basically with that, we could sort of remap or redefine the boundary of the influence of the great artesian basins. Other examples that we mentioned is that using combinations of cations and anions. In this case, it's the arsenic gold deposits, and it matches really well arsenic gold sulfide with our area, and we sort of find that there is a gold deposit, the Lorena deposit in that region. That's a borehole. The Fipsy borehole has really good indication for gold mineralization in that area as well. So it's not discovered yet, but it's potential there. Next, I know I'm running out of time. I'll just sort of go through. Not all chemistry would show up. This is an example from Kennington, thanks to Danny and his team, for allowing us to collect there. You see, it picks up silver, but not lead itself. However, we have tied in, we have the collaboration of the QUT to look at lead isotope. What the lead isotope picks up more than what the actual chemistry picks up is that the lead isotope identifies all lead in the Kennington area. The blue areas are the all lead, and you see spots of all lead around the margins of Mount Isa. The red are the younger leads, the sort of probably Cambrian and younger leads in that area. And we are still researching, trying to sort of figure out, to make sure it's younger lead itself. As it is, it's a real powerful tool because you need only one sample to tell you whether you get an old lead or a young lead in that area. And if this is true, if it holds true, groundwater just breaks the whole sort of exploration, limitations by just taking one sample, look at the lead, and then identify if you get, sort of a protozoic lead there. I'll just sort of try to sum up. This is the results of what we have come out with the different associations. We have identified 13 areas in the East Isa blocks with different mineral associations. The report will be out early next year. And so I think I don't have time to go through every one of them, but it will show new areas for exploration in the East Isa region. That summary just sums up what I've said, that it's really important to tie your new data against a backdrop of regional data. And you can't use data on its own. And the data could be used singularly as an element or combine it with anions to look at the mineral association, metal indices, metal saturations, and the importance of anions and oxyanions in that. So if you have any interest in future, of this exploration technique, you could either talk to myself or talk to Nathan, and we'll sort of guide you on the right track. Thank you very much.
Any questions for Joe? Steve.
Good, Steve.
Hi, Joe. Thanks for the talk. Really interesting. Slightly different topic. We were discussing this morning how you might get really reliable hydrogeochem samples from deep, from an exploration drill hole. So I'm talking about 800,000 meter depth of exploration drill hole. Is there any protocol for doing that reliably?
The first problem, if you got a deep hole, you had a problem, you need a submersible pump to push enough water up. And the water, it's a static water. It's not sort of, it's like we find that from exploration hole, a lot of the hole, when it's purged, when it's got refilled, it shows really low content. We don't know why, but it's probably it hasn't interacted long enough with the rock itself. So I don't know. If the water is properly equilibrated with the country rock, it's definitely a go. If it's not, if it's sort of mixed like some of the exploration hole that we done, pump it out and then get a recharge, it's really low in content. Yes.
Thanks for the talk. I have a question. Quite a few of the samples show an anomaly, and some of them seems to be close to known ore deposits, and some of them probably indicate other possible deposits. So my question is, did you try to link these anomalies with processes? So what actually cause and how these processes that cause these anomalies can be linked to mineralization? So we know that it's not just random variations that can happen.
One of the sort of main issue with hydrogeochemistry is we do not know where the water comes from. And we are a bit disappointed that, like the Kennington is a good example. We know we are sampling, above some of this region, but lead tends to flocculate. One of the problems with lead is that it has a low solubility. And if you throw in a bit of sulfate, it just flocculates and get out of solution. And so that understanding, I think, is something that you really need to look at the other elements in association with that element itself. Say, if you've got a high sulfate, you'd expect to have a low lead. And so not always that, next to a mine, you get high results. And it's the collective chemistry that actually determines, whether it's effective or not.